Hey, John here. It's time to start jotting down these ideas of the type of peripherals I want to include in my Z80 Nouveau project. And every time I do a project, I get to a point where I'm kind of like listing stuff up like this. And I got to go shopping in order to find out what parts I can use. I mean, is it reasonable to piezo speaker? I mean, sure, I can find one, right? If I want to put a USB interface on it, should I use a CH340 or an FTDI or whatever? So this is kind of like the part where I want to say I would like these features and then kind of figure out what chips are available, how big they are, what kind of packages, footprints they have, do a little shopping, and then start, cobbling together a board design, see what fits on the board, what makes sense, what's practical. If I run out of pins on the FPGA, I mean, there's only so many things I got to hook up, what stays, what goes. This is kind of like this point in my mind where that sort of thing starts to happen. As always, a big thanks to everybody that supports my channel, especially the VIP patrons listed here. Thank you very much. So the first thing I'm thinking here is the regular joysticks, like the old days, the Atari joysticks. I mean, they're fun and they're cool, and they're, that's the retro feel and all that from the 70s, early 80s. But they're hard to hold on to after a while. They're a little bit painful, and it's kind of hard to have multiple buttons. You just have the one thing and maybe a fire button or one on the top. While, the NES controller, the gamepad type of device that has, multiple buttons on both sides, and sometimes they got trigger clicky buttons on top. You get more control over those things. So I think it might be fun to go with the NES. It's also a great bit of fodder for if you're getting started on FPGAs. This is a good little interface to work on. It's relatively simple, and it should be attainable by just about anybody. So that might be a great thing to implement first, and do a test bench, test case for it, plug in something on a breadboard, test type of thing. I think it'll be pretty cool. Similar to that, we have PS2 interfaces for things like a keyboard and a mouse. And if the Nouveau, I'm thinking it might be neat, I don't know. Again, let me know in your comments below. To shoot for maybe a console, not a console per se, but a standalone unit to make my version of, back in the early days, once the S100 bus systems got expensive and started running their course, and memories got cheaper and very much bigger. You didn't need all those boards, and the likes of Apple and Radio Shack with a TRS-80, and then, your Commodore VIC-20, your Commodore 64, your MSX, and the various BBC systems. Those started beginning, standalone box type systems that maybe we could look at making something along those lines with a lot of I/O and interfaces on them that we all play around with. Which gets me to the keyboard and the mouse. Not that anybody had a mouse on a system like that back in the day, but if we were to do a PS2 type interface, I'd certainly be foolish not to allow both, because they both really work the same way in terms of what we would have to do hardware-wise, voltages and stuff like that. So if I'm going to do a PS2 keyboard, we'll throw in a PS2 mouse as well. I mean, I don't know what we'll use it for at this time, but it's something we can do. And the PS2 interface is kind of like a rite of passage when you're learning FPGAs in a university setting. You've got your PS2 interface, the UART interface is another one you do a lot of, and a VGA interface. We'll get there in a second. These are very common lessons and homework projects that are assigned in a lot of universities, and this is a great thing for us to look at here because there's going to be an enormous amount of slide decks and write-ups and even homework probably all over GitHub if we run into a problem or I explain it like a fool and you need extra help. Like I said, these things are all over the place, and we can easily find great examples of all of them and make sure that it's just a wonderful learning experience, in my opinion. We can definitely make these things happen. I'm figuring we have a bunch of pins somehow for just generic GPIO stuff where we can hook up servos, maybe add quadrature inputs and stuff like that. I don't know. I just threw these down, the first things that came to mind. Not the sort of things you'd normally find on a home computer back in 1979. But, whatever. We can certainly hook up just about anything we want on parallel pins on the FPGA that we don't use otherwise. Certainly we can have general purpose IO types of things. Certainly LEDs and stuff like that. The breakout board that I use for the ICE 40 already has 8 LEDs on it, but if we're going to develop if we're going to ultimately aim for a big board that just has a bunch of stuff on it that could be used as a PC of that era, when PC became the IBM thing, but a personal computing device, we could say, something VIC 20-ish, Commodore 64-ish, that kind of a thing. With, some status LEDs would be cool. Piezo speakers are dirt cheap. We'll get a bunch of these. We'll figure out what kind of sounds we can get out of them. I didn't put this on the retro, and I probably should have put one on like the VDP or something so we can get some kind of a sound out of it. I missed that very quickly. It was very depressing that, you're trying to build a breakout game or a Tetris or something. Just a couple of little simple, stupid, silly beeps would have been nice. Definitely not going to skip that this time, okay? So let's make sure we can make some sound and maybe even have a headphone jack. I don't know. We can shoot for that. We can certainly look at what it would take from the FPGA design standpoint, of what it takes to make sound, maybe some simple square wave type of things. We could look at how the oldie-timey sound chips worked, because they were basically generating square waves and Class D audio. If you don't know what that is yet, what you're doing here is you're basically using pulse width modulation running at frequencies much higher than what you would hear, and you vary the duty cycle to create an analog output. It's a digital to analog converter style. We can look at this as an FPGA project as well. We can even make it come out of the piezo speaker, although these generally don't have a great response curve. They make some frequencies much more audible than others, okay? Which is why I'm like, well, maybe we can throw together a really simple, cheesy audio circuit in there with headphones jacks or line out. We can hook it up to stereo, something like that. This might be fun to do, even if it doesn't end up on the whatever the Nouveau becomes. We can certainly do this on a breadboard and have some fun playing around with this in Verilog for sure. Another rite of passage in the college courses are UARTs. Everybody makes a UART in the FPGA, and while we don't need one for the Nouveau because we have UARTs on the Z80 180 chip, we might want to look at this if we want to play around with something like RS422 or 485. We can play around with DMX512. We certainly don't need it for DMX512. We might want to look at synchronous, is I guess where I was going with that mind tangent. Synchronous signals of some kind, and implement a UART that works that way. If you wanted to do something with SDLC or HDLC, that sort of thing. I don't know. Just a thought. Regardless, if we wanted to put a CH340C or an FTDI chip or something like that on there with a UART in the FPGA, or just wire it right into the Z80 180 console serial port, so that if you don't know what this is one of those chips that converts the TTL level RS-232 type signals to USB. So we can just plug a USB connector into this if we want to see serial data on a host machine. This would be convenient. AC97 and I2S, these are probably not as useful on an 8-bit system than they would be on a more modern machine. And I say that because these require a lot of data, and it's unclear to me whether this would be any fun or even useful. I mean, we can, they're certainly cheap enough. I got an I2S chip in mind. Maybe we'll throw it together on a breakout board or something and see what happens. Get it to go, see what it takes to keep it going, because we're going to have to move, a lot of data into it over the course of time. And it may end up being, just a nightmare to keep the thing going from the Z80 180. On the other hand, this chip might be something that we can play around with and generate loops inside the FPGA, not unlike a Class D type audio output. These may be related in some useful way. We'll certainly look at it. Even if it turns into a dead end, it might be fun to play around with. We might learn something. A real-time clock, battery backed up, I should say, real-time clock. This is going to be very useful if we want to implement an operating system that has a file system that has timestamps on their files. It'd be nice to have a real-time clock in there. And I'm thinking of a little chip with a little battery on it, kind of a thing. We can set it and leave it go. And that will be nice. Even if we don't use it, it'll be, again, another one of these learning exercises. They usually have like an I2C type interface or an SPI interface on these kinds of chips that would be fun to play around with as an FPGA project. Now we get to the VGA interface. This, I think, is going to be fun. This is really where this is what pushed me into the Nouveau in the first place. We're playing with a retro and the VDP on there and all of its shortcomings. There's a challenge to this. We had some games playing around with it a little bit, but how much time did I really want to spend on that before I move on to something else? I had my fun. And it works, and there's a couple of games out there. Guys did some really great work, and maybe we'll come back and revisit it at some point down the road. But I really like the idea of hooking up VGA. Composite video is just not pretty. It really is ugly. It's uglier than I remembered. Let's go to VGA. This we can go any resolution we want, really. Even with a simple cheapo FPGA that I've used here, the ICE40 HX, this can get us a lot of fun mileage. And an R2R DAC is a really simple little circuit. It's been done to death. There's tons of that out there on the web. Just go ahead and Google R2R DAC if you want to know now where we're heading with that. Basically, you just take parallel output bits from your FPGA and run them through a bunch of resistors, and voila, you've got analog output. And we will probably end up putting some simple amplifiers on that analog output, because VGA, the video lines, the red, green, and blue color signals are terminated with 75 ohms, so we may have to put a driver amp on there. This might be a fun little project. Look at interfaces and stuff like that. Again, there's a lot of these floating around on the internet. We'll do our version, see what we get out of it. And I couldn't help but notice that if we're going to do VGA, we're going to generate some timing signals and then the red, green, and blue color signals. And it turns out that DVI and DVI encoders that you can go out and buy for like $5 can be interfaced to what is, for the most part, VGA signals, and certain VGA timing, variants of the VGA timing, are supported by DVI, and DVI is electrically what HDMI is based on. So if we do this right, we could put an HDMI connector on this thing. Now, I've got plenty of video monitors around that have the DB15 VGA jack on it, so I certainly don't need this, but it might be cool. Certainly worth playing around with, even if it's going to be done in, some Franken project where we cobble together some boards. I ordered this the other day. from what, like 1-bit squared or something like that. I think somebody on the Discord was using this same board, if I can get it out of here. In fact, I think it was the Wiggler. Hey, Wiggler, how you doing? Wow, it's a lot smaller than I thought. Oh, it's tiny. What is this? What did I do? Order the wrong one? Oh, no, that's it. Wow. Oh, this is awesome. I thought, okay, this, wow. So here's a box opening that I'm shocked about. This is awesome. Wow. Wowie wow. So there's my HDMI. The one that they showed had 2 of these headers on them, and it had to go into 2 separate PMOD inputs. This is only a single PMOD. This one has, when you order the board, you specify, do I want 4-bit color, 24-bit, 12-bit, what amount of bits per pixel do you want to use? And I don't even remember what I ordered. What is this? Icebreaker PMOD 4-bit DVI. I have absolutely no idea what we're in for here. I'm going to have to go read the manual. But the point is, these chips, is this a Texas Instrument one here? I got it in my magnifying glass. Well, this is a silicon image chip. Well, I hope we can do that with the camera here. That should generate, obviously, HDMI from a PMOD output. And this is going to be fun to play around with. This is going to be pretty cool. My point is that, I think this is going to be $5 or $10 for this chip here in quantity 1 from DigiKey. Less if you buy it from, your eBays and stuff like that. And this here is $1 or something like that. So, if you really wanted to, I think we can hook up the digital signals that I'm going to use to go into this DAC here without the DAC. I think it can go directly into this. And I'm excited that there's only one PMOD connector on here because it'll be real easy to plug this onto my Ice40 HX breakout board. This is super awesome. I think it runs on 3.3 volts. Yes, it does. And it's a standard PMOD pinout. So you can see on here, I don't know if you can read that with a camera right here. I'll have to get out my new microscope camera in a minute here. A lot of light glare there. There we go. So you can see HS, interrupt, and when you got clock, green, red, blue, display enable, vertical sync, horizontal sync. This is very much similar to what you got with VGA. VGA is analog in these format, but the horizontal and vertical sync I think are going to be the same thing. And the red, green, and blue, I suspect what we do is we put multiple bits in a row. We'll probably put 4 bits of green, red, and blue per pixel out or something like that. I don't know. We'll find out. I honestly thought that this was going to be in parallel, where I would send out 1 clock per pixel. This might need 4 clocks per pixel, which makes me a little more nervous because we can only run that FPGA so fast. The slowest VGA clock speed is 25 megahertz. This would have to then therefore run at 100 megahertz, which we can easily do in the Ice40, but yeah, whatever. It's fun, right? So anyway, my point is I'm shopping here for ideas. Maybe we can build capable or compatible with that, and we can figure out what's going on there. So these are some ideas. Let's go over to DigiKey and see what all the parts that make up these interfaces might cost. Here's DigiKey. I've taken the liberty of filling in some stuff into a cart here. What do we got here? So this actually is a one of these parallel VGA looking chips. This is on one of the variants of that 1-bit squared board we were just looking at a few minutes ago. This is a product that is going out of stock going out of available last buy date in 627 like tomorrow. And I'm going to go ahead and order a couple of these at $4 a piece. These are also available, pin compatible from TI for a little more money. But I'm going to go ahead and just throw a couple of these in my cart now in case I want them to play around with. Because I think it'd be pretty cool to just slap this baby on that motherboard, or at least fill out, footprints and everything so that you could, if you wanted to, put one on there. I'd certainly like to try it and see what happens. We can test the idea, and we got to work on the Verilog if we want to, using the board that I ordered. And we can hook that up to the breakout board just to see if we like it. All right. If I don't, well, okay, fine. I got some chips sitting around that I might not use. Like that's never happened before. So that's the idea here. This is the I'll make my own version of the HDMI output DAC with this chip here kind of idea. All right. So what else is in here? This is an SD RAM. The idea with this one is this is going to be a challenge. I'm thinking that, this is what is that? 128 over 8 is what? 16 megabytes of RAM. Quantity, one price for $1.89. Okay? Now, that's an insane amount of memory to stick on a Z80. But it might be fun to see it. Well, first of all, this is not a trivial chip to interface with. This is not a static RAM that's just parallel and you can just slam the read-write output enable and have the thing go. This is a dynamic RAM, which means, and not only that, it's synchronous, which means you have to give it an address, and then a few clocks later, you can exchange data with it. And that is an interesting bit of complexity, but it might be fun, in my opinion. This might be an interesting thing that I could use for a video RAM. I mean, again, it's ludicrously huge, but it's also ludicrously cheap. So I'll throw a couple in the bag, and maybe I'll make a breakout board, or I could just, a lot of FPGA boards have these on them. This is another one of these rite of passage type of college homework assignment, is implement an SD-RAM controller. Even if we don't want to do one, we can probably find one that we can just use floating around the internet if we wanted to try it out. And you never know. It's just... It's cheaper than the DAC chip that we were just looking at for this guy up here for HDMI output. So these are kind of, let's call this a stretch goal. Maybe we can fit these on the board. Maybe we can do something useful with them. With this much memory, we might be able to load all sorts of interesting patterns and stuff in there and build some sort of a graphic accelerator board or something like that. This is very much not retro. Okay, very much not retro. But it might be an interesting project. If not today, then maybe, next year or something. In any event, I'm trying to amortize my shipping charges here by throwing a few extra doodads in. That's really what's going on here, okay? What do we got going on here? MOSFET, N channel, the BSS 138. Now, I've got a whole bunch of MOSFETs around, but they got a really crappy threshold. The VGS TH, this number right here. See the 1.5 volts right there? If you're going to buy a MOSFET and you're going to use it in a switching mode, like I did on the Flash Programmer I2C voltage, translator in the Z80 Retro, I needed... I kind of cheated. I didn't use this particular MOSFET. I used another one that had a little bit higher VGS, but I got away with it. This one is much more comfortable at 1.5 volts. Point is, I can hook this up to my FPGA running at 3.3 volts, and if I say go on, it will go on. If you use like a 2N7000, or what is that, 2700? The 7000, the one that I used on the Retro Flash Programmer, were right at the limit of its operating capability. I'm surprised it works as well as it does. This is a better choice. It's also surface mount, so I can put more of these in a tighter space. I want these because if you Google around for the PS2 port, here's the Wikipedia page for it. If we want to hook up a PS2 keyboard, it'll have a connector like that on it. Or, we'll see in a minute, it could have some USB keyboards are also PS2 compatible, and you can just grab the data lines, the USB data lines, and use them as a PS2 keyboard. A lot of keyboards have that capability. We'll experiment with that at some point as well. My point is, the PS2 interface is one of these rites of passage. We'll do this, we'll make it go, and we should be able to get it to work even on some modern keyboards. What's my point here? I've derailed myself. 5 volts. This is supposed to be a 5 volt interface. I want to hook it up to a 3.3 volt FPGA. Therefore, we're going to need voltage translators on the data line. So we're going to need to have some chips of some kind, MOSFETs to make that happen. That's why I'm getting these. These are 5 cents a piece. Wow, let's shell out $5 to have a 5-year supply. I don't use these in enormous quantities. This will last me at least a year if I just got 100 of them. Done. What's this down here? We're working ahead a little bit. Let's go to this one and then come back. This here, I got this idea from, Adafruit. This is a chip-style device that has 2, you can tell by this number, the NX1388, and this one down here is a BSS138. Well, what this is a single NFET. This is 2 NFETs on one device. Now, it's also 5 times more expensive. Not that I'm going to go to the poorhouse paying 25 cents for a part, but I don't know. I'm back and forth. I threw a few of these in the bag. We got a price break. If you go to 10, I bought 20. What this is 2 NFETs on one device. Adafruit uses these on their voltage translator boards for some product that they sell. And I was poking around over there, and it looks like a good idea. It's going to have all the same characteristics, VGS, TH of 1.5 volts. And you can see in here we have 2 NFETs in one package. Got some anti-static protection. Oh yeah, this is interesting. So the point is it has ESD protection. That's nice because MOSFETs can fry. We have to be careful how to use these things if we're going to plug them into plug external devices into these, and that's what we're really doing. And these are hot. Well, actually, the PS2 keyboard is not really supposed to be hot pluggable, but people oftentimes do use them that way. Point is, you need to make sure that we're not going to fry this thing. So this is probably a good idea. We'll have to look at this to make sure these diodes are all facing in the right direction and that do provide us with proper ESD protection in the way that we're using it. It might protect itself, but it may not protect anything else, is my point. And to that end, we've got some other things in our basket. These guys here. Okay, what do we got? A TVS device. Now, these stands for transient voltage suppressor. Let's look at this. Now, if we're going to hook up external devices, and they're going to have long cables, like, say, the gamepad and stuff like that, right? You could end up getting some static on those cables, and it could cause a problem and wreck the chips in your system. 50 cents a pop for 1, 35 cents a pop for 10. This thing, the way these work is if you, I was expecting some sort of a neat schematic drawing in here. What happens is, you see, for USB and DVI, HDMI, and all the other, the idea is that you put this between a signal and your ground. And if there's any static on here, it shorts that sucker out to ground when it's over a certain voltage. And inside here, what do we got here? Typical 14 volts. Anything over 14, it will start shunting it to ground. Clamping voltage 35. What do we got? Trigger voltage voltage capability, 8,000 volts, blah, blah, blah. What kind of capacitance it puts on there? Very little. Because this is actually going to distort, right, your signals and stuff like that. So I thought I'd throw some of these on here. They're probably a good idea. We can certainly design it in. Whether we populate it or not is another thing. Maybe what we can do is build a board. And, I mean, I don't want to blow one up, as it, it takes a long time to solder these in, and I don't want to wreck my FPGAs and stuff like that. Well, maybe there's something we can do with an oscilloscope on something, and we can experiment around to see what kind of spikes we get with and without one of these things installed. Just maybe a good idea. The idea is you put these on communication lines that leave a device if there's going to be a long cable, because you can pick up static and stuff like that, especially in the wintertime when the humidity's low. We'll run across some wool carpet or something and touch it, and the next thing you know, you might blow up your awesome project. So this will potentially, theoretically, protect us from that sort of thing, or at least help. I don't know. I've never used them before. I read about them a lot, but this will be the first time I'll try. It's surely going to be easy enough to just throw it in there. We'll see how these are used when we get to drawing up our design. Point now is to find one that's got a reasonable price, figure out what kind of footprint this has. I mean, otherwise, how am I going to design for these things, right? Do I really want to use the single MOSFET or a double one? I don't know. For now, I'll just throw them in a cart and we'll figure it out later. Now, we are going to plug in things like the joystick, the gamepad, and a PS2 keyboard and stuff like that. If that shorts out, I don't want to fry my power supply on my project, right? Now, maybe you don't really care. Power supplies these days are pretty resilient. If you did short it out, you'd essentially be in the same situation as if you simply lost power, right? If you're shunting your 5-volt bus to ground. Okay, great. Probably isn't going to kill the FPGA or something like that, but it would be nice to put some kind of a fuse, a simple circuit breaker-like device, in line. And I got a couple of them, 250 milliamps, 100 milliamps. We got a half amp here. So what these things are, let's look at one of these. They're all going to have the same data sheet probably. They just have different current ratings. What these things are going to do is as the current goes up to the rated level, well, in this case like 250 milliamps, if it goes up there or beyond it, what'll happen is this thing will automatically have a very large increase in resistance, okay? It's like a varistor kind of a thing, but a very steep curve. So what'll happen is as you get to your, these current ratings on all these things, as you get up there, this thing, you see where it says positive temperature coefficient? What happens is as the temperature goes up, the resistance goes up. Oh, I guess I thought there'd be a nice graph in here. It's linear. Power rated circuit. Oh, that's for derating. If the room gets really hot, you have to derate the value of the component. There we go. That's what I'm looking for. Time to trip is this. Fault current is that. How long does it take to trip the device for each one with all the different current ratings? How long does it take to trip the breaker for the resistance to skyrocket, right? So as you come closer and closer to the rated current, it takes less and less time before it trips, and it is logarithmic. That's what I was expecting to see. Time to trip. Some of these are higher current than others, and they have different curves. That's all this says. Okay, so what happened, that's how to solder it in. Okay, so we got to look at the darn tables. Okay, well, the idea is that it heats up when current increases, right? So here's one that's 100 milliamps. Maybe this is the one in my basket. I don't know. The hold current, the trip current, maximum voltage is 30 and it kind of goes down if you get a higher current one. This is like a 2 amp one here, right? The holding current. As you go from holding to trip, that's where you're in that logarithmic graph. So this part here, when you get to 50 milliamps, it starts to enter the zone where it starts to trip and the resistance will start going up. So in a quarter of a second, what is the maximum time to trip? If you got 1.5 amps, it'll take very little time. And the resistance goes from 3 ohms when it's working normally up to like 50 ohms. Is that true when it's tripped? R1 max? That might actually be the non-tripped resistance. R1. Maximum resistance of device at 23C. That's not the trip temperature, measured 1 hour after tripping or reflow soldering. For 20 seconds. Now maybe that is the maximum resistance when it's tripped. Power dissipated. Current max that it can withstand without damage. Well, that's not a very big resistance. Well, we'll all learn something. When we hook it up, I'll just hook these up and start ramping the current up and see what happens. I would expect the current or the resistance to be much bigger than this. What am I looking at? Those are dimensions. Huh. Well, they're not too expensive. Certainly worth trying out and see what they do. Maybe there's some better ones. I don't know. I tell you what, if you're watching this and you got some great ideas, let me know. I won't check out this basket. Let's hear what you have to say. I really like to know. I've never used, I could say, I would like to say I've never used these before. I have used these before, and not this brand. I have some little fuse ones that are these poly resettable fuses that I've used in other projects. And I know I've tested them by shorting them out. I don't know. What's your favorite brand? What do you think? If I'm hooking up like PS2 keyboard or even, Super Nintendo gamepad or something, what is your favorite proposal for me to throw in one of these fuses? Anyway, I thought I'd throw a couple in here, a couple of bucks, no big deal, and we'll rate them for our own use. Hook them up, heat them up, see what happens. It might be something worth learning. Now, I wanted to get a couple of these USB connectors. There you go. This guy, a dual USB Type A connector. Now, I'm not going to build a USB host interface. That's not the point of this. What I'm thinking is, if you go in here and look at the PS2 here, I don't know if the Wikipedia page says. What do they got here? What do they got? Here's a PS2 female to USB adapter. That's not really what I'm looking for. That's related. I got some other. But if we Google for USB to PS2 keyboard adapter schematic, there's 2 ways to make this work. As I mentioned or alluded to earlier, you can, here's a nice drawing. Let me see if we can see this thing here. Go here. There we go. Come on, 80 clicks later. Go away. So, yeah, they have both genders in here, but this is the one I'm really looking at down here, right? And I've got some of these. We'll play around with them. But the thing is, and I've even got the connector, like a PC board right angle, a PS2, host connector that this would plug into, this being the same jack that would be on a regular old PS2 keyboard, right? And it goes into a slot that looks like this that you saw on this page here. These things. I got some of these things sitting around, okay? Now, if we put 2 of them side by side on a PC board, it'll burn up an inch of space, right? 2.5 centimeters. On the other hand, if I put one of these double stack jobbies on there, that's not even 1 centimeter wide. and I could put both a mouse and a keyboard up right on top of each other. That's a space saver, and it might even be cheaper than a regular PS2 connector anyway. So that's what I'm thinking, all right? Now, in order for that to happen, okay, that's the key. What we need to know is what's in here. Well, this is not compatible with every single keyboard and every single mouse. But many keyboards, if you plug a regular USB keyboard into here, and it simply takes the two data lines out of the USB connector and the two power supply lines out of there, and just stick them in the PS2 connector like this. What happens is, and again, this is entirely the keyboard doing all the work here. It can, in many cases the keyboards do, detect that it has been plugged into a PS2 interface instead of a USB interface, and it starts squawking the PS2 protocol. So, I'll have to try some of the keyboards I got around the house, maybe hear all your opinions. I would love to have opinions on this. Is this a terrible idea to just put USB connectors on here and plug in a keyboard and a mouse into here and assume that most keyboards today still play this game where they automatically shift gears into PS2 mode? I don't really know if that's common anymore. I don't know. I'd like to, if I can get away with it, is my point. Plug in this, put this on the PC board instead of putting two of these buggers on there. I'm just saying. These things can't be right up next to each other anyway. They can only be so close because the overmolded plastic part of these connectors, I've got some that have really big connector housings on them. And even this might be too close together if you had a motherboard with them this close together. Sometimes you can get these two stacked up on each other as well. And even DigiKey sells those, but they're several dollars, which is kind of a ripoff in my opinion. I don't know. It's just a thought. These are pretty close together. Nice dense packing. Whatever. I threw a few of these in there. That's what I'm thinking for that one. This is a digital audio DAC, okay? This thing is 260 or something. I just threw one in. It might be fun to play around with. See if I can get the FPGA to make it squawk or something. It might be fun. This is obviously purchasable from Wolfson Electronics. So what do we got here? This is, your standard, CD quality digital to analog converter type of thing. And what do we got in here? This is a block diagram, and what they have is two DACs, so it's stereo, and you only need these 4 data signals going out of this thing, and you're done. Power it up. It comes out with analog output. These are basic line level outputs. So this is RCA, phono jack kind of a thing. You can plug it into your stereo if you want. I don't know if it's loud enough for headphones, but we could put some really simple class A type analog amplifier out there with a couple of transistors or something, so you can run your headphones with it if you really want to. And this is kind of a neat thing. I think it has I2C, a mute and a mode, digital filter, line ground, TP, CB, A, B. Well, that's a charge pump. Okay, when this thing runs, it needs to have a plus and negative power supply. So it has some fancy power supply stuff in here. And it's sort of like the RS-232 level converter that I put on the Retro, because it has to have plus and 12 volts in order to run. This has the same kind of thing in here to generate its own positive and negative values so that the audio can be AC coming out of here instead of DC. And this over here, what this is it's not I2S, I do not believe. Device description. If you look down here, it says when you run it, B clock, A clock, mute, blah, blah, blah. Oh, it is I2S. This has different protocols that it supports, is I guess the point here, which is why it doesn't just call itself an I2S DAC. It can run in that mode if you set this to 1, okay? if you set it to 0 or 2, or I'll let it float rather, that's a Z. It can use different encodings of which bits mean what in the serial bit stream. And that's very handy. So this could run in simple I2S mode if we want. And then down here, there's some waveforms. This will be fun to play around with the FPGA. Maybe we'll make a breakout board, or I go find one or something. I'm sure there's something like this on a PMOD board if you don't want to solder one together. But I like designing the boards and seeing if I can get it all to go myself. It's not about having it. It's about building it as far as I'm concerned. So that's why I'm throwing one of these in there. And if I'm going to design a board and I'm going to order a board, the shipping cost 5 times more than the board. So if I have to design 4 boards, it's like I'm getting 3 of them for free. So we can go ahead and throw in a couple of homebrew designs to see if we can make this thing go. Flip through this manual. This is a whole project in its own self. And you can see the encoding in here. The bottom line is you clock out your analog, you clock out the digital value of what the analog is supposed to be. Over the course of time, there's a clock signal, there's a serial. It's not unlike kind of how the SD card works. And you've got, it free runs continuously, by the way, because why wouldn't it? Audio doesn't start and stop all the time. This will free run. The B clock is the bit clock. The LR clock says I'm now sending you left data, I'm now sending you right data, and so on. And then the various bits that comprise up the analog audio sample, the digital sample for the analog output, is what you clock out synchronized to the B clock signal. This will be kind of neat. We can certainly generate square waves and things like triangle waves with really simple FPGA designs with this thing. And we'll play around. We'll learn something out of it. All right. So I'm excited, but I don't know if, like I said earlier, if this chip, because it's going to run 192K bits a second, I mean, certainly I doubt we're going to dedicate a Z80 to stream data out from its RAM. It'll probably deplete the whole RAM in less than a second. So this may be very impractical to put on a Nouveau board. On the other hand, if it's entirely operated by the FPGA, we might have something. I don't know. It's just a thought, and it's $2.50. Throw it in there. What's this? Here's your real-time clock. Why did I choose this one? Why did I choose any of these chips? I just rummaged around through DigiKey and did sorts and sorted them based on price, and I saw other people using the same chip or a similar chip, and I just went over here and grabbed them. So this is just a first draft. I'm not married to any of these. Love to hear your comments. Please send them over if you have any thoughts, good or bad. All creative criticism more than welcome on my channel. So anyway, I bought this one is because it's cheap. A lot of these are really expensive. The key here, before you start throwing 800,000 opinions, is that this is battery backed. There's a cheaper set of these clock calendars that are not battery packed. They'll free run, but you have to continuously apply power to them. Now, you have to continuously apply power to this as well. However, this one has a circuit built in. It's with the chip itself to control the battery and automatically switches itself over. You don't have to do that for it, okay? In order to run, it needs to have a 32.768 crystal. I have a bunch of these lying around, so I'm not going to buy any more. If we get to the point where we're playing around with this, I certainly let you know what the order numbers are of the ones I have. But there's really no need to buy any more. I literally have a whole bunch of these sitting around somewhere. And I did originally acquire. I know I got them from DigiKey in the past, so shouldn't be a problem. Whether it's series or parallel, you need to have the right kind. 6 to 9 pico, farad, Chris. I'm sure these are all. This is going to be an incredibly common crystal to have. It'll run on various voltages. Battery backup voltages 1.3 to 5.5, which means you can use one of those coin cell batteries to run this. And we'll see I've got some sockets for those in the shopping cart as well. So this one looked to me that it's a pretty reasonably priced one, relatively low. It talks I2C, which gives us a reason to play around with I2C on the FPGA. It gives us the clock and the date and time with battery backup. I think it'll be a pretty cool thing. And down here, I'll tell you, here's how you hook it up. Throw some resistors in your crystal in like so, and you're in business. There's the registers in there, how to access them, how to use I2C, what its address is, and how to squawk at it and stuff. It'll all be in here. So at some point, we'll play around with that. We'll see what's going on. How much are these things? 85 cents? Yeah, sure. What did I do? Buy 10 of them? I bought, what do I do? I threw 4 of them in here. If I use one, I'll use it on some other projects as well. So that's $3 worth of stuff. Here's a coin holder. Now this is 20 millimeters. 2 centimeters is a big piece of junk to have on my circuit board. I don't know if I want to waste that much real estate to hold this thing. This is a generic photo. I think all the coin cell of this style connector holders from whoever makes this thing, Atom Tech, with that style, they have the same picture on every single one of them. So this one is really big, is my point. And I don't know if I want to waste the space, but it's 20 cents. So I got a handful of them on there. We'll see what it looks like. We'll give it a sanity check. Yeah, this thing is just huge. There's a 20 millimeter battery plus the extra housing around it. I mean, this is going to weigh so much. Oh, yeah. This thing is huge. 2.5 centimeters. This is an inch. No. I mean, this is probably not the one I want to use, but we'll throw it in there for $1.79. We'll have a look-see at them and see what we think. HDMI connectors are a dime a dozen. Not quite. They're $1 a piece. A dozen for $12. $1 a piece. So what, I got a couple of these. No flange. They have these. Let's open up the data sheet for this. This will be an interesting design problem. If the KiCad library that I'm going to use doesn't already have a footprint for this, this is going to be one of those lessons in looking at the documentation very closely. HDMI connectors have an odd number of pins on them, is my point. And I've looked at this from different vendors, and for this particular one, you got to come down here. Why they do this, I don't know. There's a data sheet here. That's the one you just looked at. That's the crappy sales sheet that no engineer gives a crap about. This one down here, is it the drawing? There you go. Is the one that we care about. That right there. When we design the footprint for this thing, this is going to be an interesting little thing. This is not symmetric. Look closely at this diagram. It's got 19 pins. No pin is on this center line. There's more pins here than there is over there. When you design this footprint, you need to be careful what goes where. Whoever drew this is also a dingbat, because there's absolutely nothing in this diagram that says that hole and this hole is equidistant from this center line with this hole and that hole over here. Now, maybe sometime between my high school, when I took a mechanical drawing class, and today, the world decided that if it's perfectly symmetric, you don't include any reference anywhere in this diagram, directly or indirectly, to tell anyone that it's perfectly centered on this center line. I argue this is stupid. Just mark it so I know, not believe, all right? So I'm going to order this, and I'm going to look at it with a caliper. I'm sure that it's symmetric, but come on, people. This is just stupid. And Tyco, whatever, Amphenol has the same dimensions and everything else, and the same stupid drawing with no indication that, no confirmation that these spike holes out here are based equidistant from the center. I mean, we all know it should be, but I prefer that it is explicitly stated. I think it's just it's bad engineering not to explicitly state that. What else we got here? One of these WizNet W5500. This is a more of an undertaking here. They're not that expensive at $367. You can buy a little plug-in board. I got some of them lying around. I happen to know, because I was on the Discord. You should join the Discord if you want to chat about all this stuff with me and a bunch of other people beyond. Again, I welcome your comments in the video below on YouTube, but if you want to jump over to the Discord, I'll leave a permanent invite link in the description below this video on YouTube, and hear your thoughts on all this as well. I got this one because some other people use these already and have drivers already running on the Z8 180. Therefore, if I don't feel like writing one, I can just use their code, or so could you. Maybe mine will stink and you don't like it. You could try another one. But if we lay it out and get it on the board, or put a header so that you can talk to this with, a generic pre-made module or something. Pre-made modules are like $10, so it's probably a perfectly reasonable thing to go out and grab. What do we got? 66 pages here. I'm not going to go through this whole thing, but I skimmed it earlier. Let's talk about what it is. TCP/IP. This is an Ethernet interface chip that talks to a regular RJ45 through you get an RJ45 connector with magnetics inside of it. We'll look at that in a minute. I've dealt with this before. I'm pretty confident that I've found one that will be compatible with this. It's another thing we'll have to learn. I'll learn something. It runs on 3.3 volts. It needs a 25 megahertz clock. No problem. SPI interface. And that's what's kind of cool about this. The whole chip sits here, and we can hook it up and squawk at it using SPI, which is a real easy protocol to implement in an FPGA. I argue it's simpler than I2C by a bit of notably easier than I2C, but it's certainly worth, again, one of these rites of passage kind of things. Inside here, it implements the full IP stack, and it has some RAM memory buffers and things like that, where it has this 32K of memory. This is a 5500. I think there's a 5300 or something like that has less memory in here. So this is the current good one. It's the big one. It's the one that all the kids are using now, right? So this will give us Ethernet over here. It'll give us like interrupts, and we can pull it or whatever we want to do and exchange and transfer buffers back and forth into this memory. And it'll implement a TCP stack and stuff like that, and automatically do its ARPing and everything else. So we don't have to clown around with all the TCP, buffer allocation and timeouts and resend and socket handshaking, all that overhead that goes on. This is cheating, in my opinion, but for whatever it is, $4, I'll take it. Maybe some other time we can sit down and we can implement a whole IP stack ourselves if we really want to. But honestly, for hobby use, this really isn't a bad price. Because even if you just bought the, what we call a PHY, the physical interface, without a whole processor and a bunch of code in here doing it all for us, it's still going to cost you the same amount of money. So this might be a kind of a happy medium. It won't go very fast, and it only has so many sockets. I mean, it has certain limitations. We'll learn all about that as we go. But for now, FYI, I threw one of those in my cart just so I'd have a couple of them around, so I might design it my own little breakout board and have some fun with it. Here's the jack I'm going to use with this. I have a whole bunch of very similar from 15 years ago. I got a whole bunch of pulse jacks. That's why I bought this exact one. This one looks like it's just a modern variation of the ones that I've had lying around for a long time. I'm throwing one of these in my cart because I already got a bunch, but I want to make sure that, because this is, I got like the 0002 or something. I don't know. I'll look it up, and we'll do an apples to apples comparison. I want to verify before I ever tell anybody I use this one, I'd like to verify that it actually works, okay? My point is, this is not just an RJ45, and it's not just an RJ45 with some lights on it. This is shielded, and it's more than shielded. There's whole transformers and all kinds of stuff inside of there. If we look at the data sheet, if you're going to squawk Ethernet, you need a bunch of transformers in there. And they make these in different ways. There's symmetric and asymmetric ones that have different things going on with these center taps, is my point. So you need to be careful that you get the right kind, and that these resistors and the 1-to-1 or 1-to-100 or whatever these ratios are the things that matter. When we get around and playing around with it, we can look more closely at the WizNet chip, and we can talk about why I chose this one over a different one, okay? And I think this includes this capacitor as well. They always, there's this, 2,000 volt, tiny little capacitor, 0.001 microfarads, is that way I think of it. 1,000 puff is going to be 0.001 micros. So anyway, the point is, this is your static discharge from the center taps to these coils to protect your circuits. So yeah, this is kind of nifty. And of course, it tells you where the LEDs are. Now, some of these, how many different variations is in this data sheet? Some of these have resistors on the LEDs built into the jack. So we'll have to make sure that, this is the one that I bought. Okay, so only got one variation. In other words, I'm going to have to put my own resistors in here. If you look at Pulse, and there's a whole bunch of them, or any other brands, some of them might have the current limiting resistors built in to the jack, is my point. If you add them externally, then these will start getting dim, or maybe if we could populate it, and if you had exactly the same jack with a resistor in here, then you can simply shunt the footprint and use the resistor that's built in. So anyway, again, we'll come back to this when we actually try it out, if we ever get there, before we all die of old age. What else we got in here? Here's another DRAM. I didn't know I had two different kinds. I do remember messing around. Here's $1.89 for 128 megabytes. Oh, I know what I'm doing here. One of these is an 8-bit bus. Let's look closely. See, 32 meg by 8. So this is twice as much memory as the other chip, but this is an 8-bit data bus, okay? The other chip that we looked at earlier up here is cheaper, but it has less memory, and it has a 16-bit data bus. Now, if we're going to hook it up to an 8-bit micro, and it has a 16-bit data bus, we're going to have to play around a few games. I'm not sure which one I want to use, but the neat thing about these is, see, this says 54T SOP2. When we get to this, when I start looking at the schematic, what I can show you is that this chip and the other one we were just looking at, the one down here, has also got a 52 or 54T SOP2. These two have the same pinout. This 8-bit one, if we open up the data sheet, I'll give you a really quick peek. If we look at it, see how it says there's an 8 or a 16? Now that's just this one data sheet. But if you look at the data sheet for both of these chips side by side, and you go in here and look at them, I don't know if there's variations here. Okay, one of these will be for the X16, and this is the X8. See all these no connect, no connect, no connect, no connect, no connect, no connect, no connect. There's 8 not connected pins in here. Down here, oh look, they're all hooked up to data lines. These are compatible footprints, is my point. So we, in theory, could route it for a 16-bit chip, and it could be compatible with both. Either one you might want to put in there. However, one of the motives to use an 8-bit versus a 16-bit chip is to not use up so many FPGA pins. We're going to run out of pins. So an 8-bit chip might be a better choice than this 16-bit jobby. All right, so this is 16 megabytes. Dirt cheap at $1.89. This one is twice as much memory, but more than twice the price. At a whopping $5. We gotta fight our battles, decide which one we want to do in here. I'm gonna go ahead and buy a couple of each and just see how it falls. So I got 4 of them here for $7. Well, how many of the other ones I got? Maybe about 2 of these, maybe. Yeah, for $10. So these are more expensive. They do have more memory on them, but they're 8 bits, so this might be easier for us to work with. Here's a battery holder. They got all these different kinds. You saw the other one earlier. This was kind of a neat one. This one will let you put the coin in sideways, so the footprint on your board is much smaller. Maybe griping about that 1-inch, diameter, gigantic circular thing. This thing is going to sit up in the air. Where is the picture of this thing? So the one that we were looking at before, it looks a lot like this, but it's this giant round thing, like this sort of a thing. This one is, there's a sort of one. This is kind of a weird data sheet. They even give us footprints? Wouldn't that be nice? Well, we might have to break out the caliper again. There it is. It looks like this. So it sits up in the air. Okay? Now, that might be real annoying if you want to keep the space above the circuit board clean, in which case you do want a flat round one like one of these. On the other hand, if you don't want to waste, an enormous amount of area of your circuit board, you want it to stick up. So what are you going to waste? Horizontal space or vertical space? I don't know. Pick one. I'm going to order a couple of each, have a look-see at them, and then we'll see what we want. I can drill the board to allow us to put either one of these in there if we want to. I could probably also put the giant annoying one upside down on the board so it sits on the back and doesn't cover up, space for, 100 parts on the board just to make room so it doesn't waste so much space. Ultimately, it's probably what I'll do is I'll route the board so you could put either one in and have it so that it works. So this is a $1.26 for that thing, and these are 17 cents for the space wasters. Okay, so something like that. I don't know why I just threw one in there, probably outrageous price. I don't know, I'll have to decide what I want. This also uses a smaller battery too, by the way. The one above was a 20 millimeter, that's a 12.5. And here's a little piezo. These things come in all kinds of different types. What you want to do if you want to pick one of these, be careful. See where it says externally driven? This thing will interface like a speaker does, and that I have to generate a waveform to make it vibrate, okay? If you got a piezo sounding device that does not list itself as simply a transducer that has an external driver, then what'll happen is it may have a tone generator inside of it, and you simply apply 5 volts and it makes a beep, but that's all it can ever do. This is more like a speaker, and that's why I chose this one. So if you look through here, it's not terribly huge. How big is this sucker? 7.5 millimeters. So with the case, what do you got? 12.6. So just over a centimeter in diameter. It's not gigantic. Big space waster. I was looking at speakers originally because I was thinking maybe we'd actually literally put a little teeny speaker on there and get a better frequency response. But I don't know. This is a really crappy frequency response is my point. But if we wanted to just kind of like make video game sounds, like retro video game sounds, this will be okay. We'll be able to hear it. Low frequencies, what are we at here? Kilohertz. Yeah, well, it's certainly, you're not going to get any bass out of this, okay? But you probably won't even hear much under, say 500 hertz or something like that. And I think the resonance, it's at 4 kilohertz. So it's like natural best resonance at 4 kilohertz. It's really designed to make a 4 kilohertz tone. but it'll make some sound on these other frequencies as well. And they give you some circuitry in here. If you got a couple of NAND gates and you hook it up like this, it'll generate it'll oscillate because you're basically hooking an inverter in a loop kind of a thing here, and it'll make a tone. Okay, great. Or we throw all this away and we just hook it up to an FPGA and generate a square wave at whatever frequency we want. Throw it through a little teeny, what is that, NPN transistor, like one of those 2N222 style transistors. You give a little current drive and make the thing vibrate, and you'll hear some tones. You know, like your microwave going do-do-do-do-do-do-do, that sort of a thing if you've got one that has multiple tones. Anyway, so this should be fine, and I don't think it costs that much. What is this thing? Yeah, 30 cents or something. This is nice. We'll play around with it and see what kind of tones we can get out of there. 10 of them for $2.73. So there's my shopping list for today. Anybody got any other ideas? Or don't do this, or this is a terrible idea, or this is a great idea? Let me know. Comments below or jump on the Discord. I'd love to hear from you. Thanks for watching. Thanks for going along with this ride. I'm really interested in hearing what your opinions are. I just gave you a bunch of mine and my thoughts on what I might do with these things and how things might all fit together. What do you think? See you next time.